This is my CNC milling machine that I built over the past few months. I should note that I'm not a designer or a mechanical engineer. In fact, I faced many avoidable problems due to my lack of knowledge, and I'm not even a machinist. I ended up creating three different designs. The first two are fairly common, while the last one is a bit rarer, but seems to offer the best compromise between rigidity and travel. I already had a CNC mill, but it wasn't very rigid and had a z-axis travel of only 10 centimeters. And when I realized I would primarily be working with the low carbon steel, I quickly understood it wouldn't be suitable. Additionally, I have a lathe, a manual mill, and these were extremely useful for this project. Unfortunately, I won't be able to include everything I've done in detail in this video because I don't have footage of everything. Instead, I will focus on the main highlights. I apologize in advance for leaving out so much, but I don't have a choice. I'm truly sorry because it's in the details that I put my heart and soul, but I will have to make peace with it. That said, let's continue with the video. The first design was supposed to be something very similar to this, so after gathering the parts, I could start working. The first step was to smooth and equalize the tubing that would serve as the base. I had to mill, reposition the piece, use the indicator, mill again, change the piece, and hope that the z-axis didn't shift. This process was repeated for 6 pieces. After that, I could drill holes and subsequently thread them. Oh, I forgot to mention that I designed the structure so that heavy welding wouldn't be necessary, which could have warped everything and increased tolerances exponentially. Therefore, I decided to use M6 or M8 screws for connections. An additional advantage of screws is that the structure can be disassembled and moved to another location if needed. The trade-off is that it makes construction more challenging. Once these tasks were completed, I could create the necessary pieces to connect motors, bearings, ball screw, etc. I made most of them with a small CNC, although it was quite labor intensive. For the z-axis, I wanted to use this cross-tactile slide that I found at home, and I have never used it. Even though it wasn't hand-scraped, it seemed very promising. However, disassembling it wasn't quick. In this clip you can see how I tried to position the ball screw to connect a stepper motor while I was wearing my Hawaiian shirt. I know it would be better to use AC servos, but I'm currently designing circuits that are able to make regular steppers closed loop. So if you don't want to miss that, consider to subscribe. The z-axis has to be attached somewhere. In my design, it's connected to the x-axis plate, so I can start drilling it in the right places, hopefully. I decided to recycle the main plate from my old CNC since 40 kilograms of steel isn't cheap, so I could drill the holes in the right places. Although I would soon discover that I had taken the wrong measurements and would have to fix everything the old-fashioned way. I wanted to build a spindle despite my poor machinist skills. Spindles are quite expensive, even though the price theoretically justifies their precision. The spindle I used so far is one of those classic Chinese models, 1.5 kilowatts, 0 to 24,000 rpm. These spindles have serious issues. At low RPM, they lack the torque to work with steel, and they have standard ball bearings inside, which aren't ideal for substantial forces. Not wanting to throw that motor away, I thought it would be a good idea to create a 1-to-4 reduction using tapered roller bearings. Here are some clips where I made quite a few mistakes. Of course, I managed to mess up the inner diameter, making it 0.05 mm too wide. So I had to use glue for the bearings. I bought the shaft with ER20 collect from AliExpress because it cost only 9 euros. I only realized later why it was so cheap. With my lathe, I managed to cut a thread on the back of the shaft. I'm really happy I succeeded because my lathe isn't exactly designed for threading. In fact, I use my hand as a clutch. I mentioned the low cost of the shaft, and indeed, upon checking the tolerances, it's clear that the inner taper is misaligned with the outer cylinder. I don't have a grinding machine that can do that job, so I try to improve the situation using the lathe. I don't have any recording of the final check, but it is slightly improved, not so much however. I had to build another piece to attach to the shaft that will connect to the pulley or gear. So now I need to make a functioning pulley. I tried 3D printing them, but the belt slipped easily and would melt from the friction. So I chose to make it from aluminium, utilizing a specific feature of the DRO. After drilling the holes, I could finish it on the lathe. This is the final result. I know the belt doesn't have a tight fit, but it should work anyway. I applied the same procedure to the smaller spindle pulley. This part was really critical because disassembling the CNC means losing a tool. If I had to make specially shaped parts while it was disassembled, it would have been much more difficult. Anyway, I leave in some clips of the teardown so you can see how it was built. I wanted to put the CNC on a very heavy base, so I decided to make a 500 kilograms block of concrete. I positioned the tubing with the rails and sliders on top. I started to mount a lead screw for the y-axis. Off screen, I spent some time trying to align it as parallel as possible to the rails. For the first time, I positioned the main plane, and shortly after, I realized that many holes didn't line up. So I spent another 3 hours adjusting everything by hand. In this case, having the CNC would have been very useful. After that, I tried to see if everything worked correctly, and it seemed to. Unfortunately, I wasn't able to film the construction of these structures. They were very challenging to build because they were large, and I had to weld them and mill them. I would also find that to position the x-axis at 90 degrees to the y-axis, I'd have to widen the holes. Now it's just a matter of assembly, although it's much easier said than done. For the x-axis, I used the rear block from my old CNC. After some testing, I noticed that the motor alone couldn't support all that weight, so I added a 1-to-3 reduction. In this first test, I wanted to mill 1mm deep with an 8mm end mill. The machine immediately showed signs of extreme weakness as it vibrated a lot. I can't imagine what would have happened with steel. It makes sense that this was so weak and I didn't realize it sooner. The length of the z-axis is huge compared to the width of the x-axis, and which creates a long lever that the z-axis struggles to handle. At the moment, I thought one of the main problems was the stability from side to side. So I added another 35 kg of steel on both sides attached to the block of concrete, just for fun. It did help stiffen the structure both in front and on the sides. Unfortunately, the lever remained the same. Since even adding those steel bars didn't help much, I thought that the problem was mainly caused by the x-axis. So I thought, since the lever is so long, I can try to build dovetail guides, as they are very rigid. And I made a tool to create dovetail guides, but it didn't go very well. So I chose to build a square guide starting from the x-axis I already had. I removed the guides and then built this fly cutter that I used on many pieces. Here are some clips of various operations and assemblies. I also did quite a bit of hand scraping, as much as I could. Despite all the efforts, the situation didn't improve much. The applied lever was still the same. At this point, I didn't know whether to give up or switch to a structure like this one. These structures are certainly the most rigid, but the trade-off is that for the same space, at least one axis has less travel. Moreover, I had no energy left to create a new structure from almost scratch. So I spent a few days reflecting with bitterness until, by pure chance, I had an idea. What if I used the entire x-axis carriage as the z-axis? Well, that would be a nice challenge, especially when the battery and the time are running low. However, this idea was interesting because it meant I wouldn't have to waste all the efforts I had made previously. So I gathered my strength and tried to design it. I wanted the realization to be as close as possible to this design, where you can see that the entire x-axis moves up and down. In this way, the lever remains constant relative to the height of the z-axis, and theoretically, the largest variable is the structure, which seems to be very rigid. This type of design has a drawback though. You cannot modify the angle between the y and z axis. So on the mill, I need to try to keep the supporting structures as close to 90 degrees as possible, which required some pretty strange setups. I'd say I've talked quite a bit and I'm definitely tired. I'm leaving many clips where I construct this final structure. They are quite explanatory on their own. And this is the almost finished structure. Unfortunately, after all these efforts, my PC with parallel port decided to die. So I used an ESP32 I found at home and installed Robit GRBL onto it. which also has a decent backlash control. I used that chip from a breakout board as an obtusolator. Unfortunately, classes started again, so I wasn't able to make much more progress. In the following weeks, I managed to stiffen it by creating this steel base bolted to the floor. And now it's definitely time to test it. I'm really happy how it turned out, but it definitely needs many adjustments. In these weeks, I managed to trim it quite a bit and reduce the spindle runout. For sure, I will make many more improvements and I will probably make an entire video on those. But now I have many other interesting projects to make, and this CNC mill will make my life much easier. Thank you very much for watching.